Happy Friday, physics fans. Today we're going to talk about waves. I did put the PowerPoint up on my website, so if you go to the PowerPoint tab, and you should see a PowerPoint entitled Waves. And I have it pulled up on my computer here at home. I skipped all the way to section 13.3 in that PowerPoint, and it talks about how a wave forms. Basically, a wave is formed by some disturbance of a medium. Let me give you an example. If you throw a rock into some water, like a pond or a lake, that rock hits the surface and it disturbs that surface, and it produces waves that propagate being the term move outward. So the disturbances move outward in that medium, the medium being water. They move outward from that point of disturbance. So that's kind of what the first slide says, is that a wave pulse is a disturbance that propagates through a medium, moves through a medium. It transfers energy without transferring the matter, and the energy can be a combination of both kinetic and potential energy. So that's think of your band students. That think of a drum, the head of a drum. That drum head vibrates and produces a sound, and that sound is a disturbance of the medium that's transferred through air being the medium. So we would not hear that sound if there was no disturbance causing that. Well, what's the disturbance? It's when you hit the drum head with the mallet or the drumstick or whatever it is, and it requires a disturbance. Your instruments that you play, wind instruments, what causes the disturbance? Well, in a woodwind, it'd be the vibrating reed causes the disturbance of air. In a brass instrument, it'd be the vibration of your lips when you blow through the mouthpiece. So flute's a different story. Even though it's a woodwind instrument, the air vibrates in the column of air as you blow across the top of it. It's kind of like blowing across the top of a bottle that causes a sound in there. The air vibrates within that column, and it produces a sound that you hear as it moves through the air to your ears. We'll talk about sound next week. We're going to do waves this week and characteristics of waves, and then we'll apply that to sound next week. So as we move on in the PowerPoint, it says a disturbance can set up what's called a sine wave. Now, those of you that have had pre-calculus may have already done this, but a sine wave basically looks like this. So a wave can have a sinusoidal characteristic, and I guess right through the middle would be the point where there is no wave. So let's say if you had a string and you just held it, and if you just held it there, the string would be at rest. So that's where my little dash line would be. But then if you started jerking it like that, like those ropes that you do in the weight room, those of you that are athletes, you're producing a sine wave in that rope, and it goes up above where resting would be, and it goes below, and it goes above and below. So you're creating a sine wave in that rope when you jerk it back and forth like that. Once again, instruments. If you tune your instrument, that wave that's produced when you blow a certain note, that's a characteristic of that. That's the frequency that you play, and we'll talk about frequency in just a second. So that's all the next one says. It says that there tends to be crests and troughs in these sine waves. You may remember all of this from physical science in 8th grade. I'm sure that you have crests and troughs. Now one wavelength would be from let's say here, if that's going up, to here. That would be one wavelength from there to there. So it's two positions that are a certain distance apart, and they're in phase with each other. In phase means this one's going up, and then the wave would be going down, and then right to here where it's going up again, that's one wave. It could be from crest to crest. It could be from trough to trough. It could be anywhere on the wave. It could be from right here to right here again. So the wave would be going back down there and then back down over there. So that's a wavelength, and it's often referred to as a symbol lambda. It looks like a little sideways, upside down Y. That's lambda. And of course, it would be measured in meters. I hope you can see that. Hopefully everything's in focus. Let me check and see if that's in focus real quick. Okay, maybe you can see it. So that's lambda measured in meters. So wavelength would be measured in meters. All right, a few other terms in the PowerPoint, and I'm going to go through this quickly because a lot of this you can just look at the PowerPoint and answer the worksheet questions. But the maximum displacement, either above or below that resting point, is called the amplitude. So that's usually measured with an A, amplitude. Amplitude tells you how much energy the wave has. I often think of this. If you're standing at the ocean and you get hit with a very small wave, a wave that has very small amplitude, it's probably not going to knock you over. But here comes a wave that's a 10-foot wave, and it's coming at you, and think of all of that mass of water that's carried in that 10-foot wave. It's probably going to knock you down because it has more energy, both kinetic if it's moving and potential because of the weight of that water that could fall down. That has an incredible amplitude to it, and it has a lot of energy stored in it. So in terms of sound, you can think how loud the sound is would be measured by the amplitude of the sound. The greater the amplitude, the more energy that wave carries. In terms of sound, the greater the sound is. That's why amplifiers in cars are used. They're used to increase the amplitude of the sound, make it sound louder. It carries more energy if it's amplified. Enough energy that it causes the windows to shake in your car if it's loud, especially those bass tones that have a lot of energy, at least in a short distance, they do. Another term is wavelength. I've already covered that one. Frequency. Frequency, often shown as a little, funky looking F, I guess, if you want to call it like that, a squiggly cursive looking F. Frequency is the number of waves per second. Frequency is waves per second. So once again, let's use the ocean coming at you. If waves were coming at you right after that, let's say there's a storm coming in and coming at you wave after wave after wave after wave after wave, the frequency would be very high. You'd be experiencing a great number of waves every second. And that's what frequency is. Frequency is often measured, you may have heard of this term before, frequency is measured in hertz. We'll talk about that a little bit later on when we get to sound, the term hertz. So you could have hertz, you could have gigahertz, megahertz, and we'll talk about that a little bit later. So the more waves that are coming at you in a given period of time, the higher the frequency. Music, once again, the higher the note you play, the higher frequency it is. The lower note you play, the lower the frequency. So a really high note, it'd be lots of waves in a given second, and then the lower the note, there'd be less waves per second. And those can be pretty small increments of difference, but we'll talk about that when we get to sound also, frequency as well. Period. Period, often referred to as T. Don't ask me why capital T, but it's period. Period is the number of seconds it takes for one wave to pass. So basically, these two are the reciprocal of each other. That frequency is 1 over t, I guess I said that right, reciprocal, or period is 1 over f. So frequency and period. A lot of times we're going to talk about frequency more than period. If you were in AP Physics, period would be very important. I'll give you an example. When you did the lab where you did the inertial balance, and you counted, I think it was 25 vibrations of that inertial balance, when you were supposed to take or predict the mass of that unknown, that steel ball. You were measuring the frequency of those vibrations. How many vibrations occurred in a certain amount of time? So you did 25 vibrations over second, vibrations per second, and you found the frequency of that vibration. So that's a good example of where you've done frequency before. All right, moving on. There is a relationship between the speed of a wave and the wavelength. So two formulas here, both derived from each other. The speed of a wave, velocity, is wavelength over period. So it's how long the wave is divided by the period, the number of seconds it takes for one wave to occur. Or if you do that in terms of frequency, it would just be wavelength times frequency. So the velocity of a wave, how fast it's moving, is the wavelength times the frequency. An interesting point about wave characteristics is a wave will move the same velocity as long as it's in the same medium. If it doesn't change mediums, the velocity of a wave in that medium is constant, if that makes sense. I saw an AP style question that said a student is dipping their foot in the edge of a pool, and it's causing waves to go out in the medium. What would happen to the velocity of the wave if they dip their foot in the pool even faster? And the answer is nothing. The velocity would stay the same. Now, would the frequency of the waves go up? Yes, but the wavelength would go down. The wavelengths would be shorter. So if you multiply those two together, you would get the same velocity as you would if they were dipping it slow up and down. So that's kind of a tricky question. But if that wave's moving through water, then the velocity is constant if you don't change medium. You probably learned in physical science in 8th grade that certain waves, not certain waves, all waves, they do change velocity when they change medium. That's what a prism does. When you shine light through a prism, it goes from air into glass, which bends the wave because the wavelength, the velocity changed, and then it goes back into air again. So the velocity of the wave changed. Moving on, there's two types of waves. The main two types of waves are called transverse and longitudinal. This is a good example of a transverse wave. A transverse wave would be one that moves like this. This would be the point where we'd go out in the hall with the big long slinky and move it back and forth, and we'd see a transverse wave moving like this. If you were to tie a string onto that, let's say you tied a bow onto that wave right there with some yarn, you would see that yarn or that piece of string would move up and down in that given spot, but it would not move forward as the wave moved forward. So that first slide said it transfers energy, the wave transfers energy without transferring the medium. So think of, here's a good example. You're on the ocean and you're sitting on a a life preserver or a float or something to that extent. Here comes a wave at you. Here you are. We'll say the pin is you. Here comes a wave at you. What do? You go up, and as the wave passes, you go back down. As long as the wave's not crashing on you and pushing you in. I'm just talking about if it's coming towards you. You go up, and you go back down. So pretend you're a water molecule, a piece of the medium, a part of the medium that the wave is transferring through. Really, the medium is just moving up and down as the wave, the transverse wave, moves forward. So the wave is not pushing the medium forward as it goes like this. It's really just the medium is moving perpendicular to the propagation. So that's what this slide says, is that in a transverse wave, the displacement is perpendicular to the propagation. Now, a longitudinal wave would be like the slinky doing like this. And basically, those are called compression waves. And in a longitudinal wave, it moves like this. It compresses the medium, and then it stretches and compresses and stretches and compresses and stretches. It moves like this, kind of like a slinky, kind of like a caterpillar that moves like this. That's the way a longitudinal wave moves. Well, that's what sound does. Sound is a compression wave or a longitudinal wave that it compresses the medium, and then it stretches the medium, called a rarefaction, and then compression, and then rarefaction, compression. So it moves in series of compressions. That's what I kind of tried to do right here, and compression and rarefactions or relaxations or stretching of the medium. And basically the medium moves parallel to the propagation of the wave, and that's what this slide says. Is that longitudinal. The displacement is parallel to the direction. And usually what I do in the hall there is take a slinky, pull back about 15 or 20 of the little coils, and then let go of it, and you'll see that compression move down to the other end where somebody's holding it. And if there's enough energy, it'll reflect off of them, and it'll start coming back. That's what an echo does. An echo moves as compressions through the air. And if it hits the surface and there's enough energy, it'll bounce off of that surface and then come back to you, and you'll hear it a little while later. We'll talk about that when we get to sound also. So that's two types of wave: longitudinal here and transverse waves here. Both have different characteristics, but you can use the same terminology for both amplitude and wavelength and frequency as well. Next is when two or more waves travel through the same medium at the same time, they may interfere with each other in a process called superposition. That's called the law of superposition, that two waves can combine. So let's say here's a wave that's moving through a certain medium, and it hits some type of boundary over here. Now I'm drawing a transverse wave. This could also be sound, but if a transverse wave hits what's called a fixed boundary, when it reflects off that boundary, it will come back inverted. Meaning, if it hits like this, I'll do it in a different color. So this is the incoming wave, if we use the term like that. So it hits the boundary, and when it reflects back in the opposite direction, inverted. So you get something that looks like this. So it's coming back this way, and then if it hits off here, it'll move back and forth and back and forth. That is called superposition. When two waves align with each other, let's say their two crests align with each other and they line up perfectly. That means they're moving with the same frequency, same wavelength, and everything lines up perfectly. when the two crests align or the two troughs align, you have what's called constructive interference. You get a total that's greater than any of the two single amplitudes. If they were to line up one crest here and one trough here, they could cancel each other out, and that's called destructive interference. But what I've drawn here is what's sometimes, well, not sometimes, it is referred to as a standing wave. A standing wave forms when a wave reflects off of a boundary, and it reflects, and everything lines up with constructive and destructive interference. These little areas right here are called the antinodes, because you have the greatest constructive interference, and these little parts right here are called nodes. And nodes are where there's destructive interference. In fact, you can set this, if we were in class I would show you this, you could set this up on a string, and these little nodes, you can actually grab the little node part, and the wave will keep, it'll keep moving. It basically looks like this system is not even moving. It looks like a wave that's standing in place. Hence the name standing wave. It only forms, though, if the frequency is perfect, if the wavelengths are perfect, if any of this is out of phase, if they're not lining up perfectly, then you just get a bunch of jumbled looking mess. It doesn't form a standing wave in there. So many materials, glass, your instruments that you play, I don't know, air for that matter. Any material has a frequency in which standing waves form, and that's called the resonant frequency. So many materials, if they're forced to, if a disturbance happens, the material will resonate at that frequency. A good example of that is the classic example of somebody breaking a glass, like a wine glass, with their voice. It only works on perfectly crystal glassware. But if you match your tone, your frequency of your voice to the resonant frequency of that glass will start vibrating at the resonant frequency. And then if you have enough amplitude, enough power in your voice to do that, it will cause it to resonate even more and vibrate even more, and so much so that the material, the glass, can't withstand that much vibration, and it can crack and break. I can't do it. You have to have a very good voice that keeps that same frequency the whole time, and it has to be strong enough, has to have enough amplitude to do that as well. I think Mythbusters did an episode on breaking wine glasses with your voice, but it can be done. I've seen videos of people doing it, but I've never seen anybody do it themselves. So I've talked about constructive and destructive interference. That's in section 13.4 of the PowerPoint. I talked about reflected inverted waves with a fixed boundary, done that. Talked about speed changing when it goes through a new medium. Talked about standing waves, what forms a standing wave, nodes and antinodes. And the last thing I'm going to talk about, and there may be a little bits on your handouts that you can do, is that when, let's say the lowest standing wave you could form is when you would have one wave coming in like that, and then the reflective wave coming out like that. That would be, that's called the resonant frequency, and that would be measured in hertz. By the way, that would be a half a wavelength. This is one half of a wavelength. If from here to here is a whole wavelength, then like one little hill would be a half a wavelength. So a whole wavelength would be like here over to here. or reflected here, back over here. So one little hump's only a half a wavelength. So if that was, I don't know, let's say that was 40 hertz, then 40 hertz would be the resonant frequency of whatever material that was. If it was a rope, it depends on many things. It depends on what the material is made of. It depends on the tension that's in that string, if it's a string. So the resonant frequency of a given material is different for the material. I just made up 40 hertz. I just pulled that out of my head and just made it up. So that would be the fundamental frequency, sometimes called the fundamental frequency of this rope or this string or this material, whatever it is. So here's the cool thing. Every resonant frequency after that is a multiple of 40. So if this is the resonant frequency of this material, then, by the way, in music and in sound, that's called a harmonic. This is called the first harmonic. So if the first harmonic is 40 hertz, then the second harmonic would be 80 hertz. And what would that look like? So if this was a rope and I was doing it very slow and it sent out a wave pulse like 1/2 a wavelength and it bounced back at a half a wavelength, I'd have to go a little higher. I'd have to do a little more frequency. And what would it look like? It would look like this. Instead of a half a wavelength, it would be a whole wavelength. And instead of 40 hertz, that would be at 80 hertz. And it would bounce back like that. So from here to here is one wavelength, and from here back to there is another one wavelength. So that would be the second harmonic, and that would be at 80 hertz. The third harmonic would simply be 120 hertz, and it would be 1.5 wavelengths. It would be like if I added another half a wavelength over here, and you'd keep increasing and increasing. So basically you'd have to keep shaking the rope higher and faster and faster and faster, increasing the frequency or the number of waves per second. But it would have to be perfect to produce a standing wave. It'd have to be perfectly 40, 80, 120 hertz, 160 hertz, 200 hertz, and so forth and so on to produce a standing wave. But that's what happens in your instruments when you play an instrument. A standing wave is formed in that instrument because the air is vibrating at a certain frequency that is the resonant frequency. Now you can change that. You change it with your fingering, whatever you're doing. Guitar strings, you change that when you tighten or loosen the strings. You change the resonant frequency of that string. Well, what's it doing? It's changing the note either higher or lower because it's resonating at a different frequency. But you kind of want that frequency to be in the right frequency for that note, because if you're off a little bit, then it's going to be noticeable for the next person by you if they're in a different frequency. We'll talk about that when we get to sound, and you band folks know what I'm talking about when you tune your instrument so that you're both playing the same frequency at the same note. But that's what happens with standing waves when they resonate at a certain frequency. And then there's some math that's in there. There's not a whole lot of math in your handouts. If there is, it's pretty simple. Probably using the velocity formula. Velocity is wavelength times frequency. There may be some math where you have to figure out the resonant frequency of a system. Remember, a standing wave will form when it's at a multiple of the first harmonic or the natural frequency of that system. But that's the basics of waves. We'll apply this to sound next week. As I said, I still need some of your handouts from last week. You can email those to me. I definitely need those. Grades have been put in the grade book already. If you've dropped those off at school, you may not see a grade yet because I haven't been out there to pick them up. I probably need to do that this afternoon. So don't send me a lot of emails and say, hey, I dropped it off at school and I don't see my grade. I'm just letting you know up front that I'll go pick them up from the school. But if you email worksheets from last week to me, you should see a grade in Infinite Campus for those. And that's all I got for you for waves. The handout should be pretty easy. I've already gotten a couple of them emailed to me before I even did my lesson here. You can use the book. A lot of the material in the handout is pretty self-explanatory. And hope you're having a great week. Hope you have a great weekend. Stay safe, and I'll see you next week.